Let's go with chapter 15, lesson number 6, natural logs. What are natural logs? Well, if you have a log with base e, these are known as natural logarithms. Really, they are the inverse of e to the power of x, and the way you write them, you can write them one of two ways. Either you can write down log base e of x, or you can write down ln x. Both of these are natural logarithms. It's the way you write them. Just like using the log button on the calculator, remember if you have a problem and you need to take log of both sides, well, you can use log. On the calculator, that's log base 10. But what we can also do is we can use the ln button. That is the natural log. That will also solve the problem. However, if you have a problem and you're wanting to solve it and it includes e, well, you're best using ln, or natural logs, to solve it. It just makes the whole process a little bit easier. Note, ln really means log base e of e, and if you end up with log base e of e, well, just like log base a of a, that's equal to 1. Let's try some problems then. Example 1, solve ln x equals 7. So the first thing you want to think about is, what does ln x mean? Well, ln x means log base e of x. So let's rewrite that. So we'd have log base e of x equals 7. That's obviously difficult to solve when it's in log form. So how do we rewrite it? Good, rewrite it as an exponential form. So take your base, draw a line at the bottom, and then draw a line at the top. So think base, bottom, top if you're rewriting this. So in exponential form, you will have e to the power of 7 equals x. Perfect. After that, you would just work that out on the calculator. So x is going to be e to the power of 7 on the calculator. If you type that in, that will give you 1096.63. Woohoo! Example 2, solve e to the power of x equals 9. So for this one, well, what we're wanting to do is find the value of x, and x is an index. We need to find some way of bringing that index down. How could we do that? We take the log of both sides. However, because e is involved, we would use the natural log. So we're going to take ln of both sides. So ln e to the power of x will equal ln 9. From there, we can use the log rules to move the index down. Remember the rule, if you've got an index here, you can move that down to the front. So you'll have x ln e, and the right-hand side will stay as it is. From there, what are you thinking with this? Good. ln e really means log base e of e, and log base e of e is equal to 1. So really ln e just becomes 1, leaving us with x equals ln 9. And then from there, again, you can just type that into your calculator, and that will give you 2.2 to 1 decimal place. Example 3, solve 4 to the power of 2x plus 1 equals 50 to 2 decimal places. So with this one, again, if you look at it, well, our 2x plus 1 is an index, and we're wanting to find the value of x. We need to find some way of bringing that down. How do we do that? Well, we take logs of both sides. However, this time, because e is not involved, we could just use log, really log base 10. Or we could use ln. Both would work. Because this is natural logs and we had the whole other lesson using log, I'm going to use ln this time. But if you try log, that will work as well. So take logs of both sides. I'm using natural logs. So ln 4 to the power of 2x plus 1 equals ln 50. From there, well, you can bring the index down using your log rules. So you'd have 2x plus 1, just put that in brackets because we're multiplying the ln 4 by the whole of the 2x plus 1. And that will equal ln 50. From there, well, we need to get this 2x plus 1 in its own first of all, so divide both sides by ln 4. After that, well, you could work that out as a decimal. Just do it to a few decimal places, it's not our final answer. From there, subtract 1 from both sides, and then divide both sides by 2, and that will leave us with x equals 0.91 to the desired 2 decimal places. Yeah! Next one, example 4. For the formula pt equals 50e to the power of negative 2t, first of all, evaluate p0, and then for b, for what value of t is pt equal to a half p0. So first of all, well, we're given pt equals 50e to the power of negative 2t, and we want to evaluate p0. So to work out p0, well, we're replacing t with 0. So on the right-hand side, replace t with 0, just like that. From there, well, what would you do next? Good, you know negative 2 times 0 is just 0, so that becomes e to the power of 0. What's e to the power of 0? 1! Good, anything to the power of 0 is just going to be 1, so really it's 50 times 1, which is going to be 50. So p0 is going to be 50. For part B, for what value of t is pt equal to a half p0? Well, remember, we just had p0 equals 50. We just found that out. That was our answer for part A. p0 equals 50. So a half p0 is going to be 25. We want to find when pt is equal to that half of p0. So in other words, 25. So you can set the pt, 50e to the power of negative 2t, equal to 25. And then from there, we want to find this value of t. From that, before we take logs of both sides, because we're multiplying e by 50, well, we're best undoing that first of all. So divide both sides by 50. That'll give us e to the power of negative 2t equals 25 over 50, which is really a half. And then from there, well, t that we want is an index, so we need to take the log of both sides to then apply our log rules to bring the index down. Would we use log or would we use ln? Sahana, what do you think? Why are you saying ln? Yeah, because e is involved. If e is involved, use your natural logs. So take ln of both sides. So ln e to the power of negative 2t equals ln a half. Good. From there, Sahana, what would you do? Good, use your log rules. Bring this negative 2t down to the front. So it's negative 2t ln e still equals ln 1 half. From there, why were we using natural logs rather than log? Good, because that gives you ln, it gives you lne, and lne, if you remember, lne means log base e of e, and that's equal to 1, so that will cancel out, leaving you with negative 2t equals ln 1 half. From there, we want to get t in its own, work that out in the calculator, divide by negative 2, and t will equal to 2 decimal places, 0.35. Example 5. When taken from an oven, a bowl of pasta cools according to the model T equals 100e to the power of negative 0.36 T when T is the temperature in degrees and T is the time in minutes after leaving the oven. What was the temperature on leaving the oven, first of all? And for part B, how long will it take for the pasta to cool to 1/5 of its original temperature? So for part A, this is the formula that we are given. T is going to be the temperature at time t. So small t is going to be the time. Well, first of all, what's the temperature on leaving the oven? Well, we know when it leaves the oven, just when it leaves, that's when the timer will start. So t is going to start from 0. So when t equals 0, the temperature at time 0 is going to be 100e to the power of negative 0.36 times t, and t is 0. From there, well, you can work that out. Anything times 0 is 0, so we get 100e to the power of 0. And once again, anything to the power of 0 is 1. Good. So you'd have 100 times 1, and 100 times 1 is just 100. So the temperature at time 0, just when it leaves the oven, when the timer starts, when it's at 0, it's going to be 100 degrees. Yeah. For part B, how long will it take for the pasta to cool to 1/5 of its original temperature? Well, for this one, we know the original temperature. We worked that out. That was 100 degrees just when it came out of the oven. So 1/5 of 100 degrees is 20 degrees. How long will it take for the pasta to cool to 1/5 of the original temperature? Well, we know we can replace the temperature then with 20. Because that is what it will be at if it's 1/5 of the original. So you can then say 100e to the power of negative 0.36 t equals this 20 degrees. From there, again, before you take logs of both sides, we're multiplying this side by 100, so undo that, divide both sides by 100, so now we just have e equals negative 0.36 t equals, divided by 100, you get 0.2. Again, we're wanting to work out t. We are wanting to work out this index. So what would we have to use? Help us out, Connor. Yeah, good. would have to use logs. So would you use natural logs or would you use the log button? Log base 10 or log base e? Yeah, log base e. Why? Good, because e is involved. So for this, take natural log since e is used here. So natural logs are going to be ln, so you've got ln e to the power of negative 0.36t equals ln 0.2. The whole point in doing that, taking the logs of both sides, is you can bring this index down using your log rules. So you'd have negative 0.36t equals ln e equals ln 0.2. And remember, ln e is just going to be 1. It means log base e of e. From there, well, this just becomes 1, so you're left with negative 0.36t equals ln 0.2. And if you divide both sides by negative 0.36, you will end up with t being 4.47, 2 decimal places. And remember, the time was in minutes. Example 6. A fire was described by the law A equals A naught e to the power of kt, where A naught was the area covered when the fire was first detected, and A is the area covered t hours later. If it takes 1.5 hours for the area to double, find k. So we're given this formula here. A, which is the area, equals A naught, the area when it was first detected, times e to the power of kt, where t is the time. Well, right away we know that the time, when that's 1.5 hours, the area has doubled from A naught to 2 A naught. So we can replace A with 2 A naught, and we can replace t with 1.5. From this, well, we're wanting to work out the value of k. First of all, though, again, if you look at it, we've got e to the power of, but we're multiplying it by A naught. What we've also got is we've got A naught on both sides. So what we can do is we can divide both sides by A naught. If we do that, that'll give us 2 equals e to the power of 1.5k. After that, well, again, we've got e to the power of 1.5k. We're wanting to work out k. It's an index. We need to find a way of bringing it down. And to bring it down, we use logs. But because e is involved, we will use natural logs. So taking the natural logs of both sides. So ln2 equals ln e to the power of 1.5k. After that, because we've taken the logs of both sides, think about your log rules. We can use the log rules to move this index down. So the 1.5k will go in front of that ln e. But, Olivia, what's that you're saying? Good, ln e is equal to 1, which means then ln e will just disappear, leaving us with 1.5k equals ln2. If we want to work out the value of k then, well, we can divide both sides by 1.5. So k is equal to ln2 over 1.5. Type that into your calculator, and that will give you 0.462 to 3 decimal places. Example 7, the amount AT micrograms of a certain radioactive substance remaining after t years decreases according to the formula AT equals A naught e to the power of negative 0.002t, where A naught is the amount present initially. If 600 micrograms are left after 1000 years, how many micrograms were present initially? And for part B, the half-life of a substance is the time taken for the amount to decrease to half its original amount. What is the half-life of this substance? So right away, well, we're given this formula. We're told AT, the amount of micrograms, is equal to A naught, the amount present at the start, multiplied by e to the power of negative 0.002t. We are also told in the question that AT is equal to 600 micrograms, and that is when t equals 1000. So we can replace AT with 600, and we can replace t with 1000. From there, if we work out negative 0.002 times 1000, that'll give us 600 equals A naught e to the power of negative 2. Remember, we are wanting to work out the amount present. We want to work out A naught. So to get A naught on its own, we'll divide both sides by e to the power of negative 2. If you work that out on the calculator, that will give you 4,433.4 micrograms. And that is what you will get for A naught. Part B, The half-life of a substance is the time taken for the amount to decrease to half the original amount. What is the half-life of this substance? So there's two different ways to think about this. Either you can go back to the last page. Well, at the start there were 4,433.4, so we can divide that by 2 to work out what half of that would be. Or, a more general way, what we can do is we can think here, well, after t, after a length of time t, you'll have half the original amount. So here, instead of AT, we've got half of this original, so really we've got half of A0. So two different ways to do this. This one is more general. So from here we can do the same thing again. Divide both sides by A naught. So really a half equals e to the power of negative 0.002t. From there, where do we go? Well, again, we're wanting to work out t, so we need to find some way of bringing that down. And we can do that by taking the logs of both sides. Because e is involved though, what would we use? Natural logs! Good, use natural logs, so you're using ln. So you can say that ln 1/2 equals ln e to the power of negative 0.002t. Remember, the whole point in bringing in logs is we can use the log rule to bring that index down. So bring the negative 0.002t down to the front of ln e. And remember, ln e means log base e of e, that equals 1, so really that will disappear. So you'd have ln 1/2 equals negative 0.002t. From there, we do want to work out the value of t, so divide both sides by negative 0.002. So you've got ln 1/2 divided by that. And if you put that into the calculator, that will give you 346.6 years to one decimal place. Example 8, let y equal y naught e to the power of kt. The half-life of y is 5,700 years. Woo. Find k, correct to 3 significant figures. And for part B, what percentage of y remains after 1,000 years? It's a long time. So for this one, we've got y equals y naught e to the power of kt. We are thinking straight away the half-life of y is 5,700 years. We are told that. And because it's the half-life, well, we know that if we're starting off with y naught, then for the half-life, y is going to be half of this original value. So it will be half of y naught. So we can replace y with half y naught. That equals y naught e to the power of k times this 5,700. That is what t is going to be when we have half the original amount. From there, well, really we're doing the same things as the previous example. Both sides have a y naught, so divide both sides by y naught. So a half equals e to the power of 5,700k. Again, we're wanting to work out the value of k. It's an index, so we can apply logs to both sides. That'll let us then move the index down. So applying logs, log or ln. Good, use ln because e is involved. We've got e in this question here. If you do that, we'll have ln 1/2 equals ln e to the power of 5,700k. From there, we can use our log rules to move that index down. So move the 5,700k down in front of ln e. And remember, ln e equals 1! Good, it equals 1. So you can replace that with 1, leaving you with ln 1/2 equals 5,700k. We know we want to work out the value of k correct to 3 significant figures, so let's divide both sides by 5,700. After that, k is equal to ln 1/2 divided by 5,700, and once again put that into the calculator, and that will give you negative 0.000122 to 3 significant figures. Yeah! Part B, what percentage of y remains after 1,000 years? So we know the formula. This is what we were given in the question. We now know that value of k. K is just going to be some constant. It's to 3 significant figures. If you're asked for it to correct to 3 significant figures, use that answer in part B. So we're using this negative 0.000122 in our answer now. We're replacing k with that. From there, what percentage of y remains after 1,000 years? Well, let's see how much of it remains. So we know we've got 1,000 years, so let's replace t with 1,000. So y would equal y naught times e to the power of negative 0.000122 times 1,000. If you simplify that index, well, you can write that down as negative 0.122. From there then, y would equal, the amount would equal the original amount times e to the power of negative 0.122. Where do we go from there? Any suggestions? James, what do you think? Yeah, work out e to the power of negative 0.122. If you work that out on the calculator, that will give you, to a few decimal places, 0.8851. Which means then that we will have the amount will be equal to 0.8851 times the original amount. And if we're multiplying the original amount by 0.8851, we'll think about this decimal as a percentage, and really we are taking 88.51% of the original amount. So the amount remaining is going to be 88.51%. And that is your answer. Example 9. A grams of a radioactive substance after t minutes is given by AT equals A naught e to the power of negative KT, where A naught is the initial amount and K is a constant. In 3 minutes, the 10 grams of the substance are reduced by 1 gram to 9 grams through radioactive decay. First of all, part A, find the value of K to 3 significant figures. And for part B, another half-life question, the half-life of a substance is the length of time in which half of the substance decays. Find the half-life of this substance. So for part A, we're picking out the information first of all. We know T is going to be equal to 3. Okay, it's telling us in 3 minutes, 10 grams of the substance is reduced to 9 grams. So we know the amount at the start is going to be 10 grams, and after 3 minutes, well, there are 9 grams remaining. Take this formula then up here, AT equals A naught e to the power of negative KT, and replace T with 3, A naught with 10, and AT with 9. From there, well, we want to work out the value of K, so we have e to the power of negative 3K, but we're multiplying that by 10. Let's undo that by dividing both sides by 10. So 0.9 equals e to the power of negative 3k. From there, to work out the index, we need to use logs to bring that down. There are no logs here, so let's take logs of both sides. Once again, because e is involved, you would use the natural logs. Oh yeah. From there, take natural logs of both sides. We've got ln 0.9 equals ln e to the power of negative 3k. The whole point in doing that, Mary Lou, is because we can... Good, you can move the index down using log rules. So bring this negative 3k down to the front. And if you do that, you'd have ln 0.9 equals negative 3k times lne. Once again, Chelsea, lne is equal to... Good, is equal to 1 lne. It means log base e of e, which is equal to 1. So that will disappear, leaving us with negative 3k equals ln 0.9. We want the value of k, so divide both sides by negative 3. So we've got ln 0.9 divided by negative 3. And once again, use this magical wee number box. Dunk, 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 and that will give you 0.0351 to 3 significant figures. Yeah! Part B. So for part B, the half-life of a substance is the length of time in which half of the substance decays. Find the half-life of this substance here. So right at the start we were given this formula, AT equals A naught e to the power of negative KT, but we know the value of K. We just worked that out to 3 significant figures. That was negative 0.0351. So we can replace that. We know after T, certain amount of time, we're going to have half the original amount. And if we have half the original amount, well, A naught is what we have originally, so we're going to have half of A naught. So replace AT with a half A naught. From there, well, again, we need to work out this value of T. We have A naught on both sides. So first of all, we think, right, we'll divide both sides by A naught. Doing that, we have a half equals e to the power of negative 0.0351t. After that, well, we can bring the index down using logs. But we need to introduce logs. Log or natural log? Good. Why would you use natural? Because e is involved. Good. So take natural logs of both sides. So ln a half equals ln e to the power of negative 0.0351t. The whole point in doing that is you can move the index down using log rules, so ln1/2 will stay as it is, and we can bring that negative 0.0351t down in front of ln e. ln e is equal to 1! Good, so you can replace that with 1, leaving you with ln1/2 equals negative 0.0351t. And to get t in its own, you know you divide both sides by negative 0.0351. And if you work that out, that will give you, to a couple of decimal places, 19.75 years. Yeah! Example 10. A mug of tea cools according to the law Tt equals T0 e to the power of negative kt, where T0 is the initial temperature and Tt is the temperature after t minutes. A particular mug of tea cooled from boiling 100 degrees to 75 degrees in a quarter of an hour. Calculate the value of k to 3 significant figures. And later on, for part B, how many degrees will the temperature of the tea fall in the next quarter of an hour? So for this one, what are we thinking? Right, well, we've got this formula to begin with. We've got Tt equals T0 e to the power of negative kt. We're also told that the original temperature is 100 and the temperature after 15 minutes in a quarter of an hour is going to be 75 degrees. So Tt is going to be 75, T0, the original, is going to be 100, and the temperature will be 15. So in that formula, replace Tt, T0, and T, and that'll leave us with the only one unknown of K. From there, divide both sides by 100, and we get 0.75 equals e to the power of negative 15k. From there, we can use our logs to bring the index down, so take the logs of both sides. Remember, e is involved, so use the natural logs. From there, you can bring the index down using your log rules. So we'd get ln 0.75 equals negative 15k ln e. What's ln e equal to? Good, it's equal to 1. So you're left with ln 0.75 equals negative 15k. Just writing it back to front so I can end up with k equals. From there, divide both sides by negative 15 and you get ln 0.75 divided by negative 15. And work that out to 3 significant figures. That will give us 0.0192. Yeah! Part B. By how many degrees will the temperature of the tea fall in the next quarter of an hour? So for this one, well, we've got our formula, Tt equals T0 e to the power of negative kt, but we know k is a constant, and we just worked it out to 3 significant figures. So replace k with that number. So our formula is now Tt equals 100 e to the power of negative 0.0192t. From there, where do we go? Well, we know it's going to be the next quarter of an hour that we are looking for. So we had the time right at the start, it was 0, and we had the first 15 minutes. We're now looking for the next 15 minutes. We want to know what temperature is going to be at the end of the next set of 15 minutes. And that will take the time down to 30 minutes. So now we can replace T with 30. So the temperature is going to be equal to 100 e to the power of negative 0.0192. Remember, that's your answer from part A, times 30. Work out this index, simplify that, you get negative 0.576. After that, well, you can put that into the calculator to work it out, and it will give you a temperature of 56.21 degrees. What we're asked for, though, is by how many degrees will the temperature of the tea fall in the next quarter of an hour? Well, what we're looking for then is the temperature from 15 minutes to 30 minutes. How far will it fall? And we know, we were told in the question that after 15 minutes the temperature was 75. So it was at 75 after 15 minutes, and after 30 minutes it worked out to be 56.21. So the difference between them is 18.79 degrees. So we can say that between the 15th and the 30th minute, or for the next quarter of an hour, the temperature has fallen by 18.79 degrees Celsius. That's all the questions. There are quite a few on natural logs, especially quite a few worded problems. It is a trickier part of the course, so I put in quite a few examples for you to go back and have a look at. Once you're quite comfortable, try some of these questions on your own, see how you get on. If you do find that you are struggling with them a wee bit, maybe go back to some of these examples. Best of luck! Enjoy!